So this is going to be a video on the first lesson of the second chapter here. This is going to be a video on reasoning, specifically inductive reasoning. There's basically two branches of reasoning that we kind of focus on, inductive and deductive. So this is the inductive version of things. So let's go ahead and get to it. I'll just make a quick mic check here to make sure it's still actually going, and it is good. So, inductive reasoning is basically reasoning that's based on past examples or events or occurrences. So for instance, if they ask to guess the next number in the pattern. So here we have 5, 10, 15, 20, and it's asking us what's the next number in the pattern here. Excuse me. So we can probably assume the next number is going to be 25. Well, why? Well, because each time it seems like we're adding 5, adding 5, adding 5. So if this pattern continues, we can pretty much assume that the next one's going to be also adding 5. This is, again, an inductive reason there because we're basing it off of the past occurrences in the pattern. Now, again, could the next number be 1500? Sure, I mean, technically it could be. But based on the past events and based on past experiences, we can probably assume inductively that the next number is going to be 25 if it follows the same pattern. Now, the result you get, like that 25 before, was called a conjecture. So a conjecture is the result or the conclusion you reach based on your reasoning. So again, here, same pattern. If we do plus 5, plus 5, plus 5, plus 5, we can conject, or we can make a conjecture that the next number is probably going to be 30, because once again, we're just adding 5 each time. So the conjecture is the conclusion you come to after you've done your reasoning, essentially. Sorry. Come on. So if we look at some of the examples here, let's see if we can't use this inductive reasoning to reach a conjecture again. So we have December, May, October, March as the follow-up visits for this person. So December, May, October, March, well, it looks like it's happening every 5 months. So December, and then we have January, February, March, April, May, so that's 5 months later. And then we go 5 months down the line, October, and we go 5 months more down the line, we're back to March. So we go March, and then we go April, May, June, July. August would probably be our next best there because that would be the next 5th month down there. So it looks like the follow-up visits are occurring after every 5 months. So 5 months after March would be August, we can assume. This one here we go, 10 to 4 to -2 to -8. Anytime we have a negative involved, I automatically think of subtraction. So 10 to 4, that's -6. 4 to -2, that's also -6. -2 to -8, that's also -6. So we can probably conject that the next one is going to be -14 because it's probably subtracting 6 each time in this pattern here. And then for this geometric one, we have a green triangle, and then we draw a triangle in the middle upside down, and then we draw a triangle in the middle of each of these upside down. So again, if we follow this sort of geometric pattern here, the next triangle is probably going to look something like this. I'm not going to redraw the next shape. I'm just going to draw it into this one here. But it's probably going to be something like this, where each of these triangles have a split in them as well. There's actually a special name for this triangle. I believe it starts with an S. It's some weird guy's name. I can't remember exactly how to pronounce it, so I'm not even going to try. But it's a special type of triangle that follows this pattern. But again, this would be kind of the result we would assume for the next triangle, is that each of these black triangles would obviously be white, but that would be the next image that we would see there. And then we'd have, again, further images down the line that we can conject as well. But that's all. If they ask you for conjecture, that's all they're asking you to do is make a conclusion based on the reasoning and the facts at hand, and your own opinion, essentially. Cool. So let's see if we can't try a few more, maybe a little bit more math related here. So it says, what conjecture can we make about the sum of two even numbers? So if we add two even numbers, what conjecture can we make? Well, let's just, again, the best way to do it is to actually do a few sums and figure out if we can see a pattern. So let's add a few even numbers. So 2 plus 4, we'll do 8 plus 10, and two more even numbers, we'll do 6 plus 12. And what's a conjecture that we can make here? So that's 6, 18, and then that would also be 18. So based on these three examples, we can probably conclude that one conjecture would be that the sum is even. Because based on our three examples here, whenever we added two even numbers, we got an even number back. So we can probably conclude or conject that the sum is going to be even. Now we can actually prove that, but we don't really prove stuff using inductive reasoning like this. We usually just make our best estimate, our guess there, because technically speaking, there could be one specific type of sum of even numbers that come out to be a negative result when you add them together, and then that breaks your conjecture. So a conjecture is really only good on the amount of examples it has backing it up and how tightly your examples fit together. So again, the sum is even would be the best conjecture we can probably make here. You could also maybe say the sum is bigger than 2 because all our examples are bigger than 2 as well. Again, conjectures aren't necessarily going to be always 100% right. You can disprove a conjecture by providing a counterexample, which we'll get into later, but it's just based on what you have seen before. So. The relationship between AB and EF, if AB is equal to CD and CD is equal to EF. So remember, these are talking about lengths of segments. So here we have a segment AB, here we have a segment EF, and it's asking us what do we know about how these two are related. Well, EF. How are these two related if we know that AB is equal to CD and CD is equal to EF? Well, this is actually something called the transitive property, and that if you have two different things, AB, EF, if you have two things and they are equal to the same item, that means those two things, A, B, and EF, are equal to each other. So AB is equal to EF is the conjecture we can make here. Since they're both equal to the same thing, that means they both have to be equal to each other. Or basically think about it as swapping out a CD with an AB. Why can't I do that? Well, they're both equal anyway, so taking CD out and putting AB in its place isn't going to make a big difference. It's like saying, what do you know about 1 plus 4 and 0 plus 5? Well, these are both going to be equal because if you say, okay, well, these are both equal to 3 plus 2. 1 plus 4 is the same as 3 plus 2. 0 plus 5 is the same as 3 plus 2. So since these two things are both equal to this one item, that means they have to be equal to each other as well. It's kind of like saying that just with geometric segments involved. And again, something called the transitive property. And the sum of the squares of two consecutive natural numbers. So again, that's one's a little bit of a jump there. It's a little bit mouthful. Natural numbers are numbers that you're typically used to counting with. So 1, 2, 3, 4, 5, those are natural numbers. And it says the sum of squares of two consecutive natural numbers. So that means if I take a number like 2 squared and add the next number squared, which would be 3 squared, or 3 squared, then consecutive means right after. So 3 right after 3 is 4. So it'd be 4 squared. And then you can do something like 5 squared right after 5 is 6. So plus 6 squared. That'd be the consecutive sum of the squares of the natural numbers, essentially. So basically it says take two numbers back to back, so like 2 and 3, 3 and 4, 5 and 6, square them and add them together. What can you say? Well, if we do this here, 2 squared is 4, 3 squared is 9, and 4 plus 9 is 13. 3 squared is 9, 4 squared is 16, so 9 plus 16 would end up giving you 25. Actually, I think I may have did that wrong. 9 plus 16, no, that's right, it would end up giving you 25. I was thinking 26 there for a second. And then we have 5 squared, which is 25, plus 6 squared, which is 36. So 25 plus 36 would end up giving you 61. So what can we conclude about these? Well, from our sums here, it looks like these are all going to be odd. So one thing you might say is that the sum is odd. So the sum of the squares of two consecutive natural numbers is an odd number. That could be one conjecture you could make. Now, some of you are probably thinking, well, that's not always true, and you're right. So this is an example of this is a conjecture that would be a valid conjecture. You can't say it's not a good conjecture because it is just your estimate based on these examples. But if we do something like, well, actually, really on down the road, since it's consecutive, if I think about this here, since it's consecutive, this actually would work. I forgot that it's consecutive, not just any natural numbers. So yeah, this actually would be a true conjecture. We can actually prove that this is true. Because I was thinking 2 squared plus 4 squared, but those aren't consecutive, so we can't add them together in this statement here. So actually, this would be a valid conjecture, and we could actually prove this conjecture if we wanted to using other types of reasoning. Now, some of you later on down the line, maybe you can find a case where this is not true. If you can find a case where this is not true, then you've disproven the conjecture, and good for you. But again, the conjecture is just a conclusion based on your past reasoning. So if this is all the reasoning you have to go off of, then this is a valid conclusion to reach. Once you get more reasoning, then your conclusion might change. So you can always alter your conjecture when there's new evidence or new reasoning presented. And speaking of which, this is how you do it. So a counterexample is simply an example that disproves a conjecture. So if you say that the sum of a positive number and another number is always positive. So if you take a positive number and you add another number, you always get a positive number back. Well, that's a conjecture, but it's wrong because we can disprove it. We can provide a counterexample. So one counterexample would be this. You have a positive number. You have some other number, which in this case is negative 10, because it just says another number. It doesn't say whether it's a positive another number. It's just another number. If I add 2 and negative 10, I get negative 8, which is not a positive number like the conjecture said it should be. So since this disproves the conjecture is proven false, essentially. So a counterexample is simply something that shows that the conjecture is wrong. At least one case. All you need is one counterexample in order for a conjecture to be completely invalid. So conjectures have a very high level of proof there. You need to make sure that's provable for every type of situation the conjecture fits. Otherwise, if you get one counterexample in there, then the conjecture doesn't work. You have to alter the way you say it at the very least. So sometimes we use terminology about specific number groups in these conjectures, so it's good to just kind of recap this a little bit right now. So real numbers are basically any numbers that you're used to working with. So pretty much all the numbers we're going to use in this course here are going to be real numbers, so not really much to deal with there. Integers are simply numbers that are not decimals or fractions. So 1/2 would not be an integer, 2.67 would not be an integer. Integers are simply non-decimals and non-fraction numbers. Whole numbers are the positive integers. So whole numbers are basically everything from 0 on up. So 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, dot, 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 dot. Those would be the whole numbers. Again, no decimals or fractions, just all non-decimal fraction numbers. The rational numbers are numbers that can be written as fractions. So basically everything except for special numbers like pi or root 2 or stuff like that, those are all rational numbers. So pi is what we call an irrational number because you cannot write pi as a fraction. There's no fraction that gives you pi exactly. You can approximate it, but you can't get exactly pi using a fraction of real numbers. Same for like root 2. You cannot make a number, you cannot make a fraction that gives you the exact value of root 2. There's just no way of doing it. So numbers that are these are called irrational numbers, but everything else is going to be a rational number. So once again, most of the numbers we work with here are going to be rational numbers. When we start doing stuff with square roots and with circles, then we'll start using some irrational numbers here and there. And the natural numbers are just the counting numbers. So if I ask you to count to 5 and you start 1, 2, 3, 4, 5, those are the counting numbers, or the natural numbers. They don't include 0, but we call them natural or counting numbers because that's typically how people would count if you asked them to count to a certain number. Cool. There we go. So let's see if we can't provide a counterexample to disprove these conjectures. So it says if n is a real number, then negative n is a negative number. So we want a counterexample to disprove that claim. That if n is a real number, then negative n is a negative number. So let's think of an n that would disprove this. So if n is a real number, well, a real number can be anything. So maybe a real number could be negative 3. That's a real number. So it says then negative n is a negative number. So if I have negative n, that would be negative negative 3. And we all know that if I have a negative next to a negative, these are going to make it into a positive 3. So I have a case here where n is a real number, but negative n is a positive number, unlike what the conjecture states. So this would be a counterexample to that. Negative 3 is an example where n is a real number, but negative n is not a negative number. Negative n is a positive number. And again, you can do this with a lot of other numbers too. 0 could be another one because negative 0 is still 0, and 0 is not considered really positive nor negative, so therefore that would also disprove the conjecture as well. If ABC is congruent to DBE, then those angles are vertical angles. So we need to have two angles that are congruent, and the conjecture says then they have to be vertical. We need to think about a case where they're not. Well, let's draw it like this. Here's A, B, C, and then maybe we have something like this here, like that, and here we have D, B, E. Now again, I didn't draw this perfectly, so you have to give me a break there a little bit. But let's say that this angle here is 30 degrees, and this angle here is 30 degrees, and in the middle is 120, which doesn't look like it, but use your imagination. So this is a case where ABC, that angle, is congruent to DBE, this angle, but they're not vertical. So this would disprove the conjecture, because I've drawn two angles here that are congruent but not vertical, and therefore that goes against what they said. So it's a counterexample, so it disproves the conjecture. There's a few other ways you could have drawn this tail. You could have just drawn two separate angles, like here. A, B, C, and D, B, E. Make this 50, make this 50, and this would be another counterexample. These are definitely not vertical because they're two complete separate angles, but they are still congruent. So again, counterexamples can come in many different forms. All you need is one. There we go. Excuse me. So make a conjecture about the following here. So the product of two even numbers. So if I take an even number times an even number, what's the conjecture I can make? So once again, the best way to get a conjecture is to look at a few examples. So let's do the product of two even numbers a little bit. So 2 times 4, that's two even numbers. 6 times 8 is two even numbers. 10 times 12, that's two even numbers. So here we get 8, here we get 24, here we get 120. So what's a conjecture we can make here? Well, once again, we can see that all our answers are even. So one conjecture we can make is that the product is even. Because based on the examples I did, which are only 3, but based on the examples I did, every time I multiplied two even numbers, I got an even number back. So I can say that the product of two even numbers is most likely going to be even. But that's a conjecture based on my inductive reasoning. The relationship, excuse me, sorry, I don't know why I keep yawning when I'm doing these things here. The relationship between A and B if A plus B is 0. So we need to think about two numbers, A and B, that add to be 0, and let's see if we can't make a conjecture about them. So 3 plus negative 3 is 0. Negative 1 plus 1 is 0. Two other numbers that make 0. 6 plus negative 6 is 0. So what's the conclusion or conjecture we can reach here? Well, we can see that in each of these cases, we basically have a number and the opposite. A number and the opposite, a number and the opposite. So the relationship I can say here is that if A plus B is 0, that means A and B are opposites. Probably spelled that wrong, but they're opposites. So again, that's just based on the three examples that I came up with there. Again, if you do more examples, you might figure out a different conjecture, or you might figure out an additional conjecture. So the conjecture isn't necessarily the entire aspect of what the problem could be. The conjecture is, what do you see as a pattern based on your past results, essentially. So what I see as a pattern here is that each time I added two numbers to get 0, they were both opposites. So that's the conjecture I make. The value of A or B if A times B is 0. So can't keep my mouth closed there. So let's go ahead and figure out some cases where this happened there. So two numbers that multiply to 0. We have 5 times 0 is 0. 10 times 0 is 0. 0 times 0 is 0. 12 times 0 is 0. So the value of A or B if they multiply to 0. Well, and again, remember, this also works in reverse. So 0 times 5 is 0. 0 times 10 is 0, and dot, dot, dot. So what we can have here, we can basically say that A or B is equal to 0. So if A times B is 0, that means one or the other has to be equal to 0, or both. So A or B, or both, has to be equal to 0 would be a conjecture we can conclude from this inductive reasoning. Because based on my past examples, the only time I was able to multiply to get 0 was if I took a number and times it to 0, or if I took 0 and times it to another number. So one of the two numbers had to be 0 in order to multiply to 0, and that's my conjecture. That one of those two has to be 0 in order for that statement to work. So, and let's see here. Let's see if we can't see if this is true or false. And if it's false, we need to provide a counterexample. So if a polygon has 4 sides, then it is a square. Well, I can actually provide a counterexample here real easily. 1, 2, 3, 4. So this would be classified as not a square, but a rectangle. It is a polygon. It does have 4 sides, but it is not a square. So these two sides are equal, and these two sides are equal, but not all 4 sides are equal to each other. So this would be my counterexample. This is a polygon, so it fits the description of the if. If it's a polygon that has 4 sides, that's this. Then it is a square. No, it's not. Therefore, this counterexample disproves that conjecture. So you're looking for a case where the if part is true and the then part is false. So if you want to make a counterexample, you want the if part to be true and the then part to be false in your example. So if an angle is obtuse, then it is 100 degrees. Well, that's again a fairly simple one to disprove. Here's an obtuse angle. We can just call it 120. 120 is an obtuse angle. It is definitely not 100 degrees, so that'd be my counterexample. So sometimes the counterexamples don't take that long to obtain because it's just a really quick picture draw. If a triangle is a right triangle, then it is, or sorry, it says say then it has only one right angle, not it is. So then it has only one right angle. Well, let's draw a right triangle here. So here's a right triangle. Is there a way I can draw a right triangle that has more than one right angle? Well, one of the rules for the triangles is that all 3 angles have to add to 90. That's one of the rules for a triangle, even a right triangle, that all the angles have to add to 90. So if I have more than one right angle, that means I'm already at, or sorry, all the angles in a triangle have to add to 180, not 90. All the angles in a triangle have to add to 180. So if I have more than one right angle, I'm already at 180. So here's a right angle here. Here's a right angle here. I'm already at 180. If I try to make a third angle here, I'm going to have more than 180 degrees, and that's going to break the rule for triangles. So this one actually is a true statement. This conjecture is true because there is no way to draw a triangle, a right triangle, with more than one right angle. Because if I try that, I end up getting a square or a rectangle or some sort of quadrilateral, essentially, or a pentagon even. Um, so in this case, that conjecture is true. There is no way to prove that false. That is a true 100% accurate statement. That in a right triangle, there is only one right angle, because any more than that, you break the rule for a triangle, and that can't happen. And again, you can just try for a few hours or so if you really want to, and try to draw a right triangle with more than one right angle, and you won't be able to do it. So this conjecture is true until someone comes up with a very creative example to prove otherwise, if it exists. So. And that's about that. So again, remember the key takeaways here is that inductive reasoning is based on past examples or events. You look at past examples or events, you come to a conclusion based on the pattern, and then in order to disprove that conclusion, you need to come up with just one counterexample, if it exists, to prove or disprove your conjecture. So again, hopefully this video helped you out. Again, you ask me if you have any questions. Otherwise, have a good day.